We're now going to define electric potential voltage mathematically. So as it says here, 3 equal signs, right? So we have an equality by definition that voltage is the change in potential energy, joules, per coulomb of charge. So joules per coulomb. So there you go. And right away now we know that 1 volt equals 1 joule per coulomb. So please make sure you get the units down there in your notes. Now, since we have delta V equals delta U on Q, that's the textbook definition. So if you open up your textbook, voltage, delta V, is always defined as delta U on Q, but we will often just use delta U, rearrange it to use delta U equals Q delta V. So that's why I boxed this over here. Just like F equals MA, we could rearrange that into a fraction, but we don't. We just use it as F equals MA. We'll be using delta U equals Q delta V. And as it says here, since the change in potential energy can be positive or negative, right? You can either gain or lose potential energy. Positive and negatives are now important, so we need to put in the positive and negative for the Q. So please make sure you get all of this annotated completely. And as we said on our first page, we will definitely be thinking of voltage as an energy pressure where a positive charge moves from high voltage to low voltage. So delta U and delta V are definitely almost the same thing, right? Because we have delta V equals delta U, and if it weren't for the divided by delta Q, they would be the same thing, and we wouldn't talk about it at all. But that's why we're saying it's like an energy pressure. It's the joules per coulomb. So it's not quite the same as atmospheric pressure, force per unit area. But in terms of just conceptualizing it, thinking about what is actually going to happen in a problem, it's very, very useful. For example, in the example we have here on this page, we're told we have a region of space where at one point we have 4 volts, another point we have 2 volts, and we are going to start a proton, so a positively charged particle. We are going to start it from rest at the 4-volt region and see what happens. Well, we know that a positively charged particle moves from high pressure to low pressure. So without any calculation, just conceptually, we know that this particle is going to whoosh, speed up, going towards the low pressure. Now, it doesn't have it here in your notes, but make sure you put it in. These arrows are not voltage arrows. Those are electric field arrows. So that is our field vector, the electric field vector, and we'll talk in another couple pages of notes about the mathematical relationship between electric field and voltage, but electric field lines always point from high voltage to low voltage. Well, we are given the change in voltage. So we know the delta V, final minus initial. So we have a drop in voltage, negative 2 volts times the charge on the electron. Remember, the positive and negative is definitely important, so we need to make sure we explicitly put in the positive and negative. So we see that we get a decrease in the potential energy. Lost potential energy, negative 3.2 times 10 to the minus 19 joules. Well, conservation of energy applies in physics, whether it's mechanics or electricity and magnetism. So then we can very quickly get the change in the kinetic energy is negative the change in potential energy. So we have our negative from our potential energy. We have the additional negative for change in kinetic energy is negative the change in potential. To get a positive change in kinetic energy, the mass of the proton is given to us here. So we know the mass of the proton, 1.67 times 10 to the minus 27. And that gives us a final velocity of a large 19,576 meters per second with just 2 volts. Because the proton does not have very much inertia, 10 to the minus 27 kilograms, it actually acquires a great deal of speed going over a voltage drop of 2 volts. Now, had we been given electric field information, we could, of course, have used F equals ma equals QE. So just like in mechanics, you don't have to use the energy approach. You can use forces and acceleration for calculating what is going on in a problem. But if we have the energy approach, it's a scalar to work with. We don't have to really worry about any vector mathematics coming into our problems. So this is the basic concept mathematically relating voltage to potential energy and how it is used numerically in a problem to calculate the change in potential energy, and then of course go back to mechanics and calculate our change in kinetic energy. And we will move on.